Ceva's theorem gave us a necessary and sufficient condition for three lines to intersect at one point. We just put the three lines in the triangle and then calculate some ratios. There is another version of Ceva's theorem called the trigonometric version of Ceva's theorem that instead of using ratios along the sides of the triangle, uses ratios of the sines of the angles here that I've marked in this triangle. This is why it's also called the sine form of Ceva's theorem. The trigonometric version of Ceva's theorem states that the three red lines intersect at one point if and only if this condition is satisfied. Sine of alpha 1 divided by sine of alpha 2 times sine of beta 1 divided by sine of beta 2 times sine of gamma 1 divided by sine of gamma 2 equals 1. Here's one way we can prove that this equality holds, given that these three red lines intersect at one point. This solution works when all the angles in the triangle are acute, and when this point is inside of the triangle. Suppose that this distance is x, this is y, this is z, and we draw perpendiculars from this point to the three sides of the triangle, and their lengths are n, m, and p respectively. Consider this right-angled triangle. Sine of alpha 1 is p divided by x. Similarly, sine of alpha 2 from this right-angled triangle is m divided by x. So when we take the ratio sine of alpha 1 divided by sine of alpha 2, the x cancels out, and what is left is p divided by m. So sine of alpha 1 divided by sine of alpha 2 is p divided by m. Similarly, for sine of beta 1 divided by sine of beta 2, we have sine of beta 1 is m divided by y, sine of beta 2 is n divided by y. The y cancels out when we take the ratio of the two signs, and then we get sine of beta 1 divided by sine of beta 2 is m divided by n. And in the same way, we find sine of gamma 1 divided by sine of gamma 2 equals n divided by p, and these three quantities are given here. Now we just need to multiply the three equalities together. On the left-hand side, we get sine of alpha 1 over sine of alpha 2 times sine of beta 1 over sine of beta 2 times sine of gamma 1 over sine of gamma 2, which is exactly the left-hand side from here. And on the right-hand side, the p cancels out here, the n cancels out here, and the m cancels out here. And so the right-hand side is just 1. Now let's try to work in the opposite direction. Suppose that we know that this equality holds, and these angles in the equality refer to the angles alpha 1 and alpha 2 defining this red line, the angles beta 1 and beta 2 defining this red line, and the angles gamma 1 and gamma 2 defining this red line. So we need to prove that the three red lines intersect at one point. So let's define this point to be the intersection of this red line and this red line, and we're going to connect this point and this point with this green line. So we have to prove that the green line and this red line are actually the same line. In other words, we have to show that beta 1 equals beta 1 prime, where beta 1 prime is this angle defined by the green line. Now we know that this red line, and this green line intersect at one point, and so we can use what we've already proved, that if we know that three lines intersect at one point, then the six angles that they make with the sides of the triangle satisfy this relationship here. And now that we know that this equality holds and this equality holds, we can divide one by the other, cancel out the alpha 1, alpha 2, gamma 1, and gamma 2, and then we'll be left with sine of beta 1 over sine of beta 2 equals sine of beta 1 prime over sine of beta 2 prime. We know that the sum of beta 1 and beta 2 equals the sum of beta 1 prime and beta 2 prime, because both sums equal, as you can see in the picture, this angle of the triangle. And now from this equality and to this equality, we can conclude that beta 1 equals beta 1 prime and beta 2 equals beta 2 prime, because it follows that the cotangent of beta 1 equals the cotangent of beta 1 prime, and the cotangent of beta 2 equals the cotangent of beta 2 prime. And we know that beta 1, beta 2, beta 1 prime, and beta 2 prime are between 0 and 180 degrees, and therefore beta 1 must equal beta 1 prime, and beta 2 must equal beta 2 prime, meaning that the red line and the green line are actually the same line. Note that if the triangle had an obtuse angle, for example here, then the solution wouldn't work quite as we described. It would still work, but it needs some adjustments. Instead, I'll propose a different way of proving the sine form of Ceva's theorem, and it would involve showing that the regular form of Ceva's theorem is actually equivalent to its trigonometric form, or sine form. Suppose you have a triangle, and these three lines, these two red lines, we don't know if they intersect at one point or not. What we know is that this length is d, this length is e, f, g, m, and n. The sides of the triangle we label a, b, and c, and the angles we label alpha 1, alpha 2, beta 1, beta 2, and gamma 1, gamma 2. We know that these three lines intersect at one point if and only if d over e times f over g times m over n equals 1. And we're going to prove that it is equivalent to sine of alpha 1 over sine of alpha 2 times sine of beta 1 over sine of beta 2 times sine of gamma 1 over sine of gamma 2 equals 1, which is the sine form of Ceva's theorem. First, let's apply the law of sines for this triangle and this triangle. We get that sine of alpha 1 divided by sine of alpha 2 equals g over f times c over b, as given here. Similarly, by applying the law of sines for this triangle and this triangle, we get that sine of beta 1 over sine of beta 2 equals n divided by m times a divided by c, as given here, and sine of gamma 1 over sine of gamma 2 equals e over d times b over a, as given here. And now we can multiply these three equalities. On the left-hand side, we get sine of alpha 1 over sine of alpha 2 times sine of beta 1 over sine of beta 2 times sine of gamma 1 over sine of gamma 2. And on the right-hand side, you can see that the sides of the triangle A, B, and C cancel out here. A here, B here, and C here. And what is left is g over f times n over m times e over d. But this expression is exactly the reciprocal value of this expression. And we know that this expression equals 1 if and only if these three lines intersect at one point. And this expression equals 1 if and only if this expression equals 1. And since this equals this, then this expression equals 1 if and only if this expression equals 1. But this expression to equal 1 is exactly the statement of the sine form of Ceva's theorem. Therefore, the two forms, the normal form given by this equality and the sine form given by this equality, they're exactly the same statement, so they're equivalent. Here's how the sine variant of Ceva's theorem looks like when the point is outside of the triangle. In the usual form of Ceva's theorem, we know that these three lines intersect at one point if and only if a plus g over g times f over e times d over d plus b equals 1 as given here. The trigonometric form is exactly the same, you just need to track the signs that correspond to each of the segments here. For example, a plus g corresponds to the sine of alpha 1 of this angle here, and then g corresponds to this angle alpha 2. Then f over e, f corresponds to this angle gamma 1, and e corresponds to this angle gamma 2. And finally, d over d plus b corresponds to beta 1 over beta 2. Beta 2 is the whole angle from this line to this red line here. The proof that these two are equivalent is the same. You just apply the law of sines for this triangle and this triangle, for example, and then you get that sine of beta 1 over sine of beta 2 equals d over d plus b times a over c, if this side here is c. Then you apply the law of sines for this triangle, and you get sine of gamma 1 over sine of gamma 2 equals f over e times b over a. And finally, you apply the law of sines for this triangle and this triangle, and you get sine of alpha 1 over sine of alpha 2 equals a plus g over g times c over b. The a, b, and c cancel out, and then you get that this expression equals this expression. Exactly the same as in the case when this point was inside of the triangle. It should be noted that there exists also a sine version of Menelaus' theorem. Suppose we have a triangle and 3 points each lying on a side of the triangle or on an extension of a side of the triangle. These 3 points lie on a straight line if and only if, as you see in the picture, c plus d over d times e over f times g over h equals 1. We labeled the sides of the triangle C, A, and B. And let's label the angles as follows. Alpha 1 here, alpha 2 here, gamma 1 here, this whole angle, gamma 2, this small angle, beta 1 here, and beta 2 here. Then it turns out that these 3 points lie on a straight line if and only if sine of alpha 1 over sine of alpha 2 times sine of gamma 1 over sine of gamma 2 times sine of beta 1 over sine of beta 2 equals 1. We can prove the equivalence of these statements by just showing that sine of alpha 1 over sine of alpha 2 times sine of beta 1 over sine of beta 2 times sine of gamma 1 over sine of gamma 2 equals this expression right here. From the law of sines applied to this triangle and to this triangle, we get that sine of alpha 1 over sine of alpha 2 equals e over f times b over c, as given here. Similarly, from the law of sines applied to this triangle and to this triangle, we get that the ratio sine beta 1 over sine of beta 2 equals g over h times c over a, given here. And lastly, by applying the law of sines to this triangle and this small triangle, we get that sine of gamma 1 over sine of gamma 2 equals c plus d over d times a over b, as given here. And hence, when we multiply these three quantities, on the left-hand side, we get the multiplication of the ratios of sines, and on the right-hand side, the b cancels out, the a cancels out, and the c cancels out, and what we have is e over f, g over h, and c plus d over d, which is exactly the same as this expression here. And therefore, sine alpha 1 over sine alpha 2 times sine beta 1 over sine beta 2 times sine gamma 1 over sine gamma 2 equals c plus d over d times e over f times g over h. And so this expression equals 1 if and only if the product of these three ratios of sines equals 1, if and only if these 3 points lie on a straight line. Here's the optional problem. This is a triangle, and this here is an altitude in the triangle. We construct this point such that this angle is a right angle, 90 degrees, and we construct this point such that this angle here is 90 degrees, and such that this angle equals this angle. Then we connect this vertex with this point, and this vertex with this point, like that, and we need to prove that the three red lines intersect at one point. And here's the solution. Let's label the angles in the triangle by alpha, beta, and gamma. And let's label this angle here alpha 1, this small angle here alpha 2, this angle beta 1, and this angle beta 2. Also, let's denote this angle by x and this angle by x. And so this angle must equal 90 minus x, and this angle must equal 90 minus x. Also, since this angle is alpha and this here is 90 degrees, we know that this is 90 minus alpha. And since this is beta and this is 90 degrees, we have that this angle is 90 minus beta. What we need to prove is that sine of alpha 1 divided by sine of alpha 2 times sine of beta 1 divided by sine of beta 2 times sine of 90 minus beta, sine of 90 minus alpha equals 1, and the statement would follow from the trigonometric form of Ceva's theorem. Let's denote this length by m, this length by n, this length by p, and this length by q. Then we have similar triangles. This triangle is similar to this triangle because they have the same angles, and therefore m divided by n equals p divided by q. Now let's apply the law of sines for this triangle and this triangle. Then we get that sine of alpha 1 over sine of alpha 2 equals n divided by m times sine of gamma plus x over sine of 90 plus beta, as given here. We can apply the law of sines for this triangle and this triangle, and then we get that sine of beta 1 over sine of beta 2 equals p over q times sine of 90 plus alpha over sine of gamma plus x, as given here. Now, because of this equality, we can cancel out n divided by m times p divided by q. We can also cancel out sine of gamma plus x over sine of gamma plus x. And now what we're left with is sine of 90 minus beta over sine of 90 plus beta, and then sine of 90 plus alpha over sine of 90 minus alpha. But we know that sine of 90 minus beta equals sine of 90 plus beta, because the sum of 90 minus beta and 90 plus beta is 180 degrees, so we can cancel out these two. And similarly, we can cancel out sine of 90 minus alpha, which is equal to sine of 90 plus alpha. And therefore, the whole expression equals 1. Hence, the trigonometric form of Ceva's theorem gives us that the three red lines intersect at one point.